Number 39. Number 39 talks about an African Bombardier beetle that can emit a jet of defensive spray from the movable tip of its abdomen. The body's reservoir has two different chemicals, so when the beetle is disturbed, these chemicals are combined in a reaction chamber, producing a compound that is warmed from 20 degrees to 100 degrees by heat of reaction. The high pressure produced allows the compound to be sprayed out at a speed up to 19 meters per second. So the velocity of that thing coming out is 19 meters per second. So scaring away the predator of all kinds. So calculate the heat of reaction of the two chemicals in joules per kilogram. So heat of reaction, let's call it delta in joules per kilogram. So let's assume 1 kilogram of the material being dealt with. Assume that the specific heat capacity of the two chemicals is the same as water. So the specific heat of the chemical is 4.19 times 10 to the third joules per kilogram Kelvin. And the initial temperature is at 20 degrees. So it's 20 degrees initially to a final of 100 degrees. So in this case, we can figure that the heat of reaction has to increase the chemicals from a 20 to 100, and then plus coming out at this kinetic energy. So the kinetic energy plus the heat required to increase from 20 to 100 will have to be all supplied by the reaction of the chemicals. So if I assume that the chemicals coming out is 1 kilogram, so the kinetic energy will be 1 kilogram times 19 squared, that's 1/2 mv squared. That energy, kinetic energy, you have to add that to the amount of heat that raised the temperature from 20 to 100, which is mCv delta T, which is 1 kilogram. Cv will be 4.19 times 10 to the 3. Change in temperature is 100 minus 20, which is 80. All that will have to come from the reaction heat of 1 kilogram. So this is reaction heat, let's say delta H. So if I assume it's 1 kilogram, then delta H is simply the sum of these numbers. So it's 1/2 19 squared plus 4.19 times 10 to the cube times 80. So I get 0.5 times 19 squared plus 4.19 e to the 10 to the cube times 80. I get a total of 3.35 times 10 to the 5th joules per kilogram. So, and if you round it to 2 sig figs, I have 3.4 times 10 to the 5th joules per kilogram. And that's the correct answer. So number 41 says, during certain seasons, strong wind called Chinook blow from the west across the eastern slopes of Rockies and downhill to Denver. So the mountains are cool. The wind in Denver is very hot. Within a few minutes after the Chinook wind arrives, the temperature can climb 20 degrees. So number A, explain why the temperature of the Chinook wind rises as it descends the slope. And why is it important that the wind be fast moving? Well, when the wind blows from top of the mountains towards the bottom of the mountain, there is elevation drop. So that will be the energy that the environment does work onto the system of air. And if the surrounding are nothing but rocks, like the Rockies, where heat cannot escape, and therefore you can consider that as adiabatic, which means heat loss is very minimal, and especially when the wind is traveling very fast. So essentially the heat loss is minimized, and therefore all the work done by the drop of elevation become the increase in internal energy of the wind, which will cause the rise of temperature of the wind. Therefore, as the elevation drops, the air will gain in temperature due to increase in internal energy, and that energy came from the system putting in work to raise the internal energy, and the process is adiabatic as there is no heat loss. So again, the reason why it is important that the wind be fast moving so that heat loss is minimized, and therefore this process can be considered adiabatic. Part B, suppose a strong wind is blowing towards Denver, elevation of 1630, from Gray's Peak at elevation of 4350 meter, where the air pressure is 5.60 times 10 to the 4 Pascal. And the temperature at the time is negative 15 degrees Celsius, or negative 15 plus 273 to get to 58 Kelvin. And the temperature and pressure in Denver before the wind arrives are 2 degrees Celsius, and the pressure P2 is 8.12 times 10 to the 4 Pascal. The temperature is the temperature of the environment before the wind arrives. Okay, but that is not going to be the temperature that the wind itself is that it carries. So, anyways, if this is adiabatic, which means heat loss is 0, assuming it's 0, and we can also assume that this is a air. So gamma for air is 1.40, which is basically diatomic. So gamma, according to the table, is 1.40. Now, because it's adiabatic, then we can say that the temperature T2 that we can calculate is related to P1. Okay, T's and P's are related through the formula by this. First, we figure out the ratio of V over V2, because there is a adiabatic process of V1 V equals to P2 V2 gamma, like so. And then what you need to do is to figure out what the ratio is between P1 and V1. P1 and P2, I mean. P1 and P2 therefore equal to V2 to the gamma divided by V1 to the gamma, or you can factor out like this. So since we know P1 and P2, we can plug in 5.60 times 10 to the 4th divided by 8.12 times 10 to the 4th, 10 to the 4 cancel. So by doing this, we now know what the ratio of V2 over V1 is to the gamma. Or you can say V2 over V1 is 5.60 divided by 8.12, all raised to the power of 1 over gamma. 1 over gamma is 1.4, so you can do that. Now then, there's another one, that is T1 V1 to the gamma minus 1 is T2 V2 to the gamma minus 1. Now then, T2 over T1 then, if I want to know what T2 is, will be T1 V1, or T1's down here, so V1 to the gamma minus 1 over V2 to the gamma minus 1, or you can rewrite this one as gamma minus 1 like so. So let's figure out what V2 over V1 divided by 8.2, all raised to the power of 1 divided by 1.4. So I get V2 over V1 as 0.7668 or 9. But then this one is actually V1 over V2, not V2 over V1. So I need to take the reciprocal of that number, which gives me 1.304. Raised to the power of gamma minus 1. Gamma is 1.4 minus 1 is 0.4. So this number raised to the power of 0.4, I get 1.11. That means T2 over T1 is 1.11, or T2 equals 1.11 times T1. And T1 is 258 Kelvin. So if you multiply the 2, you get 286 or 286.9 Kelvin, which is the same as 13.9 degrees Celsius. So the temperature of the wind that's being brought down is 13.9 degrees Celsius. And so they say that by how many Celsius degrees will the temperature in Denver rise when the Chinook arrives. So therefore, if it was 2 degrees, then 13.9 minus 2 degrees that it started with, it should go up by 11.9 degrees Celsius. Because the wind itself is 13.9, and original, before the Chinook arrived, it was 2 degrees Celsius. So subtract the 2, you get how much increase the air in Denver will have to so that the final temperature will be 13.9. So that is 41. So number 43. An air pump has a cylinder of 0.25 meter long with a movable piston. So imagine here's a cylinder of 0.25 meters long. And the pump is used to compress air from an atmospheric pressure of 1.01 times 10 to the 5th Pascal into a very large tank. So it is connected to another tank which has a gauge pressure of 4.20 times 10 to the 5th. Gauge pressure means the pressure in the tank above and beyond the air pressure. So that if the gauge pressure is 0, it actually means that the pressure in the tank is the same as air pressure outside of the tank. Basically, that means there's no more pressure. So gauge pressure is really the excess pressure of the air inside the tank compared to the air outside of the tank, or compared to the air pressure. Now, for air, the CV is 20.8 joule per mole Kelvin. So, question number A, the piston begins the compression stroke at the top end of the cylinder. So, how far down the length of the cylinder has the piston moved when air first begins to flow from the cylinder into the tank, assuming the compression is adiabatic. So this is adiabatic compression. So the piston is at the very top first, and then as it comes down, it's going to increase the pressure within the cylinder. The only time that the air from the cylinder will go into the tank is if the pressure in the cylinder is in fact equal to the pressure inside the tank. If it is greater, then you will start flowing. So at least it has to be equal in order for it to begin flowing. So the question then is, how far down does it have to move so that the pressure in the cylinder will now begin equal to the pressure in the tank? Well, the pressure in the tank is really the gauge pressure plus air pressure. So pressure in tank is 4.20 to the fifth plus 1.01 times 10 to the fifth. So is 5.21 times 10 to the fifth Pascal. That is the pressure, absolute pressure in the tank. Now what you need to do is figure out, and therefore in order for the air to flow, this in the cylinder, it also has to be 5.21 times 10 to the fifth. Now this is the adiabatic compression. So initially it's air pressure, which is 1.01 times 10 to the fifth Pascal. Now at the end, after the adiabatic compression, P2 is 5.21 times 10 to the fifth Pascal. So they say, well, how much should it compress? Well, if this is adiabatic compression, then you have two formulas you need to memorize, and that is P1V1 to the gamma equal to P2V2 to the gamma, and T1V1 to the gamma minus 1 equals to T2V2 to the gamma minus 1. And gamma in this case is adiabatic, and for air, it should be 1.4. So that you look up, okay? Now, since you're given these two pressures, so you can then calculate the ratio between the volumes. So P1 is the beginning, so I say P1V1 gamma equals to P2V2 gamma. Then I can say, okay, P2 over P1, okay, move the P1 underneath here, and therefore V1 to the gamma divided by V2 to the same gamma. So I can factor out, or I can use the same exponent gamma here. And this is P2 is 5.21 times 10 to the fifth divided by 1.01 times 10 to the fifth, so 10 to the fifth cancel. So this number is really 5.21 and divided by 1.01 is 5.158 or 1.56. So that is the ratio. But then V1 over V2 is now 5.16 to the exponent of 1 over gamma, which is 1 over 4.0. So I can figure out V1 over V2 now by raising this number to the power of 1 over 1.4. So I get a 3.228, and that is the ratio of V1 versus V2. Or you can say V1 is V2, or V2 is V1 divided by 3.228. Now, V1 is basically the area of the cylinder on top times a height of 0.25 divided by 3.228 is the area of the top times the height here. Okay? So we can now cancel out the h's, the areas, figure out what h is. H is basically 0.25 divided by 3.228. So I get a height of 0.0774 meters. So therefore, the amount of height that you need to compress or move the piston by will have to be the total height of 0.250 meters minus 0.774 meters. And then I get 0.25. So I get 0.172 or 173 meters. Therefore, the piston has to move down 17.3 centimeters or 0.173 meters. Same thing. So that is part A. And part B, it says, if the air is taken into the pump at 27 degrees Celsius, what is the temperature of the compressed air? So initially, temperature is 27 degrees Celsius. So it's 300 Kelvin. What is the final temperature of the compressed air? Well, then we know that the ratio from T1, T2 is using the formula here. So I can write T2, V2 to the gamma minus 1 is T1, V1 gamma minus 1, or T2 over T1 is V1 over V2 all to the power of gamma minus 1. We already know that V1 over V2 is 3.228. So I can write 3.228 raised to the power of gamma 1.4 minus 1, so 0.4. So 3.228 raised to the power of 0.4, 1.60. So this is 1.60, 1.60 times 300. I get 479 Kelvin, which minus 273 is 206 degrees Celsius. So that's correct. And then part C says if how much work does the pump do in putting 20 moles of air into the tank? 20 moles of air into the tank. Well, if it is adiabatic, then you know that there's no heat loss. So all the work done is due to internal energy. Right? So change in internal energy in this case is NCV delta T. And we have figured out that N is 20. CV, we were told, is 20.8. Change in temperature is 206 minus 27 times 20.8 times 20 moles. So I get 7.46 times 10 to the 4th joules. And that's correct. So that's how you do 43. Okay, 45. A monatomic ideal gas expands slowly to twice its original volume. So monatomic ideal gas expands twice of its initial volume, doing 300 joules of work in the process. So work done is 300 joules. Find the heat added to the gas and the change in internal energy of the gas if the process is isothermal. So A, if the process is isothermal. B, if it is adiabatic. And C, if it is isobaric. So they want you to figure out what the heat added. So Q equals to what? And the change in internal energy, delta U, equals to what? Okay, so if it is isothermal, which means no change in temperature, so delta T is 0. If it is isothermal, if delta T is 0, that implies immediately delta U is 0. If delta U is 0, then Q will have to be same as W. Since W is 300, so is Q. Therefore, Q is the heat the environment adds to the system. So in this case, the answer will be 300 joule. And what is the internal change? None. 0. So that's part A. Part B is adiabatic. Adiabatic means no change in heat. And therefore, the internal energy will have to be the negative of work done. Therefore, the answer is no change in heat. Delta U is just negative of 300 joules. Okay, so internal energy has broken down to afford the 300 joules of work to be done. So this is if it is adiabatic. And part C is isobaric. Now, if it is isobaric, then we need to use the concept that Q is NCP delta T, isobaric. That means constant pressure. Okay, and but constant pressure, there is still delta U plus the work done. But under constant pressure, delta U is actually NCV delta T, and W is just NR delta T. So since this is given to us as 300 joules, we can therefore figure out what delta T we're talking about. So for example, 300 joules is NR delta T, and so we can now figure what N delta T will simply be 300 over R. Now R is 8.31, so N delta T will be 300 divided by 8.31. I get a 36.1, which means if I come over to here, the delta U is simply NCV delta T, or N delta T, CV, and N delta T we already figured out is 36.1. CV for monatomic ideal gas, according to the table, is 12.47. So 36.1 times 12.47, I get a 450 joules as the internal heat. Okay? Well then, therefore, the heat, internal energy, therefore the heat will therefore be delta U plus work. So the 450 plus the work of 300. So altogether, 750 joules. So therefore, if it was isobaric, the heat added to the system is 750, and the change in internal energy is 450, and then the work of course is 300. So that's it. Seems to be all correct. And number 47. Number 47 says, use the conditions and processes of problem 17.46 to compute. Well, that means we have to do 17.46. So let's do 46, then we do 47. 46 says a cylinder with a piston contains 0.25 moles. So N is 0.25 moles of oxygen. Oh, this is diatomic. So we can write down a few things. If it is diatomic, we can write gamma for oxygen is 1.4. Cb, we might as well write that down, 20.85. Cp is 29.17. This is all for oxygen only. So now the oxygen is at a pressure of, so P1 is 2.40 times 10 to the 5th Pascal, and at a temperature of 355 Kelvin. So the oxygen may be treated as ideal gas. Okay, so ideal. The gas first expands isobarically to twice its original volume. So we can actually draw the PV graph. Now first draw some examples of isothermal. Now if the gas first expands isobarically to twice its volume, so let's say I have somewhere here that this is V1. It looks like this is about V2, twice the volume. So it goes from here to here. Let's call this one A to here, B. So the process goes from A to B at the pressure of P1. So it goes from A to B, and then it says it then the gas first expands isobarically to twice its original volume. It is then compressed isothermally back to its original volume. So which means this is original volume. Oops, sorry, here. So it's actually from B along the isothermal graph. So from here to a point C here. Okay, this is P2. We don't know what it is, but it is now back to the same volume as before, except it is following this isothermal graph. And then from C it says finally it is cooled isochorically to its original pressure. That means from here down to here. Isochorically means same volume down to here. Okay, so number 46 says, now show the series of processes in the PV diagram, which is what I've just shown, and B, compute the temperature during the isothermal compression. So in other words, what is the temperature here? I call it T2. I know T1 is 355, so this is 355 K. We need to know T2. And what's the maximum pressure? What's P2? So T2 equals to what? P2 equals to what? That's the maximum pressure here. And they also want you to figure out the total work done by the piston on the gas. Well, total work done is really the area underneath this isothermal, which is the entire thing. Well, you have to minus the area underneath the AB or the isobaric, so that the real area that you're calculating is just the shaded area here, in almost like a triangle. Okay, it's not a triangle. It looks like a triangle, but it's not a triangle. So let's figure out what T2 is. First, this is isobaric. P1 from A to B. Now we know from isobaric is that the work done is just nR delta T, and that is the work done, or P delta V. Okay, but let's figure out what V1 is. P1 V1 equals to nR T1. Okay, we know T1, which is 355. We know P1, which is 2 times 2.4 10 to the 5th. So from here we can figure out what V1 is, which is nR T1 over P1. So if you plug in all the numbers, 0.25 times 8.31 times the temperature of 355 divided by pressure of 2.4 E fifth, I get a 3.07 times 10 to the negative 3 cubic meter. That's V1. Now when the volume has doubled, so V2 is basically double that, which will be 6.14 times 10 to the negative 3 then. Okay. Well, just by doing this, I now can figure out the work done. The work done is the graph below the isobaric. So W is P delta V. Okay, P is 2.40 times 10 to the 5th. Delta V is V2 minus V1. Since this is twice as much as that, so the delta V will simply be 3.07 times 10 to the negative 3. So now I can figure out what the work done is. 2.4 to the 5th times, well, that's it. So the energy is 737.5 joules, and that will have to be the same as nR delta T. So I can now figure out what delta T is. Delta T is 737.5 divided by N, 0.25, and 8.31 for the R. So divided by 8.31 divided by 0.25, I get a delta T of 355 Kelvin. So that's a change in temperature. Okay, that will be what this is. 355. Oh, sorry, is that 355? Okay, so that means that 355 is the change plus the original, which is also 355. So the T2 then just be doubling that, 710. So this is actually 710 Kelvin. Okay, T2 is 710 Kelvin. So knowing T2, I can actually say that the temperature here is also 710 Kelvin because it's isothermal. So T2 now is 7110. So that's first answer A. They want to know P2, which is up here. Well, since it's isothermal, I also know the volume, V1. I know the temperature. So P2 is simply nRT2 over V2. N is 0.25, 8.31. T2 is 710 divided by V2, which is 6.14, 10 to the negative 3. So my pressure is 2.40 times 10 to the 5th Pascal. So that's my part B answer. Okay, so that's maximum pressure here, 2.4 times 10 to the 5th. So the last question is, what is the work? Compute the total work done by the piston. Well, total work done is really the area underneath the isothermal, and then minus the area underneath the isobaric, just the angle triangle shaded. So the work done throughout the entire cycle will be the area underneath the isothermal, okay, minus the area underneath the isobaric, just so that it will be completely within this encircled area. The area underneath isothermal, so the work done for isothermal is nRT ln V2 minus V, or divided by V1. Now, depending on what direction you're traveling. So since I'm traveling from V2 to V1, from here to here, so my final is this one. So N, which is 0.25, R 8.31, T, the temperature is 710, ln of V2, which is in this case is the final. Okay, V2 in this case means final. So the V2 over V1, well, we know that V2 over V1 will be 2. Oh, sorry, V2 in this case is the final. Final over initial. Final is V1. V1 over V2 is 1/2. So let's see what we get. 0.25 times 8.31 times 710 times long half. I get a negative 1022 joule. Now it makes sense because as you go from right to left, your area is considered negative. So work done is negative 1.22 joule, and then there's no change in internal energy. Delta U should be 0. So the heat added back in should be the same as negative 1.22 joule, or heat is now flowing out of the system. Anyway, so that is the work done, but then there is no work from C to A. That's isochloric, so that's no work done. And then the net, of course, you have to subtract this part. So negative 1.022, well, in this case, is actually positive. So, and that we calculated earlier was 737.5. Therefore, the net, the total, should be negative 1.22 joules plus 737.5 joules. So a net of negative 185 joules. So that means that the amount of work that is done is actually from the system to the environment with net work of 285 joules. So that is for question 46. So we can do 47 now. So 47 is a continuation of 46. 47 says use the previous question to compute the work done by the gas. So work done by the gas, the heat added to it, Q equals to what, and the internal change. First they want to figure out during the initial expansion, which is from A to B, and then they want you to figure out everything during the last cooling phase, which is isochloric from B to A, and then finally they want you to do the same thing for the B to C phase, the isothermal. So basically, we just need to write all these out for different processes. First, from A to B, if you remember, from A to B is isobaric. The work done we already figured out was 737.5. So the work done, 737.5, that's the work done from A to B. And the internal energy change, the internal energy change is and CV delta T. N we know is 0.25. CV we know is 20.85. Change in temperature we know was 355. That is the change in temperature. So this is therefore delta U. So 0.25 times 20.85 times 355. I get internal energy of 1,850 joules. So the Q is therefore 1850 plus 737.5 joules. So again, the total heat is 1588 joules. So 1588 joules is the total heat added to the process from A to B. Internal energy is 1850 joules, and then the work done is 737 joules. Okay, so that is from A to B. Okay, from C to A, which is the isochoric one, well, work done is 0. There's no work done vertically. Isochoric, there's no work. But the change in internal energy is again NCV delta T. In this case, N is the same, CV is 20.85, but delta T is negative now because it's from high temperature to low temperature. That is, the final temperature is 355, initial temperature is 710. So 0.25 times 20.85 times bracket 355 minus 710. I get a negative 1850 joules. So that is the change in internal energy. And heat, therefore, is change in internal energy plus work. So it's simply 1850 joules. There is no work. So that is the from C to A final step in the cycle. And then the last one they want is to find the B to C, the isothermal stage. From B to C, isothermal delta T is 0, so we can right away say delta U is 0. And the work we calculated earlier to be for the isothermal, we calculate the work to be negative 1022. So negative 1022 joule. Therefore, heat will be 0 plus that is also negative 1022 joule. Okay, so the last stage, again, heat is 1022 joule negative. No internal change in energy because it's isothermal. And then the work done is negative 1022 joule. If you add up all the heat, okay, of all three stages, negative 1022 plus negative 1850 plus 2588, let's see what total will be 2588 plus negative 1850 plus negative 1022. Let's see what we get. I get a negative 284 joule. Now that is the heat. Now since heat is negative, that means the system is releasing the energy to the environment, 284 joules. And that was also basically the amount of work of 285 joule as well that we figured out earlier. Okay, so that's 47. So question 48. First, question 48 says, a cylinder with a piston contains 0.15 moles of nitrogen. So nitrogen, 0.150 moles of nitrogen, which is diatomic, and then you can look it up on the table for nitrogen. CV equals 20.76, CP is 29.07, gamma is 1.40, so these are all just data. So the cylinder with a piston contains that many moles of nitrogen at the pressure of, so P1 is 1.80 times 10 to the 5th Pascal, and at the temperature, T1, of 300 Kelvin. The nitrogen may be treated as ideal gas. So gas is first compressed isobarically to half its original volume. So V1 we don't know, but V2 is 1/2 of V1. So if you graph the PV diagram, okay, let's say I'm going to draw an isothermal first, maybe a few. Now, first they say that it is first compressed isobarically to 1/2 the original volume. So let me pick this point. It seems to be good. So from this point A to this point B, it is V1. So this is actually half of V1, or called V2. Okay, so from here to here, that's the first process to have its original volume. then it expands adiabatically back to the original volume. Okay, so adiabatically, which means it's actually steeper than the isothermal. So I'll just pick a point here where this is adiabatically from B to the point C in order to reach the same volume. Okay, now this pressure here will be the lowest pressure. Let's call it PC, and this is PA, or in this case P1. One and A and B will be the same. And then they say that finally it's heated isochorically to its original pressure. So this one now goes back up from C to A. So that is the entire process. Show the series of processes in PV diagram, which I did. Compute the temperature at the beginning and at the end of the adiabatic. So this part is adiabatic. So they want to know the temperature at, say, TB here, and at TC. Okay, TC will be lower, TB will be higher. So compute the temperature at the beginning and end of adiabatic, and compute the minimum pressure, which is PC. So they want to know all this. Okay, first we can figure out V1 because we have all the information here. At the very beginning, we know P1 already. We know T1 or TA, which is 300 Kelvin. Okay, so P1 V1 equals nRT1 or TA. So in this case, we can figure out V1 is nRTA over P1. N is 0.50 mole, 8.31 for R, TA is 300 K, P1 is 1.8 times 10 to the 5th. So we get a volume of 2.078 times 10 to the negative 3 cubic meter. Now immediately we know V2, which is half of V1, so take that divided by 2. V2 is therefore 1.039 times 10 to the negative 3 cubic meter. So I know this one now. I also know P1, so I can now know TB, the temperature, which is P1 V2 over NR. P1 is still 1.80 times 10 to the 5th. Volume 2, which is this number, 1.039 times 10 to the negative 3, all divided by 0.15 mole, 8.31 for the R. So we get 1.8E5 divided by 0.15 divided by 8.31. So I get 150 Kelvin. So this TB is 150 Kelvin. Now it's going to be adiabatically compressed. So its TB is 150 Kelvin. And we need to know what the TC is. But because this is adiabatic, there are two formulas will come to mind for adiabatic, and that is P1V1 gamma equals to P2V2 gamma. So right there we can figure out what the PC is. Okay, so that will be PC here with a V1, and this will be in fact P1 here with a volume of P2. So in this case, PC will therefore be P1 V2 gamma divided by V1, all gamma. So P1 is 1.80 times 10 to the 5th. V2 divided by V1, we know that V2 is only half of V1, so this is just half. Gamma we know is 1.4. So 1.8E5 times 0.5 raised to the power of 1.4. We now know the pressure is 6.82 times 10 to the 4 Pascal. And we can also figure out, so that's PC, 6.82 times 10 to the 4th Pascal. And TC, well, TC and TB are also on the adiabatic curve, and we also can use T1 V1 gamma minus 1 equal to T2 V2 gamma minus 1. If I know T1 already, which is TB, okay, so this is, if I write this properly, at this location is TB, the volume is actually V2, which is half of V1, to the gamma minus 1 is equal to this point, which is TC, we don't know, times V1 to the gamma minus 1. So we need to know what TC is. So TC therefore equals TB, and then this one, V1 over 2, all to the gamma minus 1, divided by V1 to the gamma minus 1. So these two cancel. So TC then is equal to TB, which is 150K, times, this is 1/2, so 0.5 left inside, to the gamma minus 1. Gamma is 1.4, minus 1 is 0.4. So the answer is 150 times 0.5 raised to the power of 0.4. I get 113 or 114 Kelvin. So TC is 114 Kelvin. So compute the minimum pressure, which we found was this number, and also the temperature at the beginning and the end of the adiabatic process. At the beginning is TB 150, at the end is 114, even lower Kelvin. So that is 48. And 49 says, use the condition and processes of this previous question to compute the work done by the gas and the heat added to it and its internal energy change during the initial compression. So from here to here, so for the process from A to B, they want you to figure out the internal energy, the work done, the heat, okay? So from here to here, it is isobaric, which means that the work done is simply all the area underneath the curve, except it's going from right to left, so this energy will be negative. So W will actually be V2, which is 1/2 V1, minus V1 times the pressure, which is P1. So I plug in P1, which is 1.8 times 10 to the 5th. 1/2 V1 minus V1 is negative 1/2 of V1. V1 we already figured out was this number, 2.078 times 10 to the negative 3. So 1.8 E5 times 0.5 negative times 2.078 to the negative 3. So I get a negative 187 joule. So that's work done. And this is isobaric. So the internal energy is simply NCV delta T. N is 0.150 moles. CV we know is 20.76. Delta T, change in temperature, is from B to A. So TB, which we found was 150 K, minus original 300 K. So that's a change in temperature. So 0.15 times 20.76 times 150 negative. So I get a negative 467 joule. Therefore, the heat will be internal, negative 467, and work done, negative 187. So total is negative 654 joules. So that is the amount of heat that is flowing out of the system to the environment, accompanied by a drop in internal energy of this much with a work of that much. So continuing, delta U, if you calculate all this, will be 0.150 times 20.96, 0.76, 0.150 times 20.76 times negative 150. You get energy of negative 467 joule. Okay, that is from A to B. And then from B to C is adiabatic. If it is adiabatic, it means Q must be 0, and delta U must be actually negative of W. But W, we know, is NCV delta T. So N is 0.150 mole, CV is 20.76, delta T, T final, which is TC, is 114, minus TB, which is 150. So we get negative 0.15 times 20 times 96 times bracket 114 minus 150. You get 112 joule. So because they add up to 0, and the work is actually positive from left to right here, so this is actually the work of 112. But then the delta U will have to be negative 112 joule, because they add up to 0. And then from C back to A, which is isochoric, if it's isochoric, which means work is 0, and the internal energy, which is just NCV delta T, will be N is again 0.150, C is 20.76. Delta T will be from TC, which is 114, to an N of 300. So 300 minus 114. So 300 minus 114, and then multiplied by 20.76 times 0.150, we get 579 joules. And Q, which is delta U plus W, so W is 0, so Q is simply the same, 700 joules. So if you add up all the heat and all the work and all the U, let's see what they should be. Okay, the first heat is actually this plus that, which is negative 147 minus 187. So negative 67 joules, 467 joules, minus 187 joules is negative 654 joules. So 654 joules, and then the internal energy is negative 467 joules, and then the work done is negative 187 joules. Okay, so these two add up to that. And then from B to C, the internal energy is negative 112, work is 112, and Q is 0. And lastly, C to A, work is 0, Q is 579, and the work is 579. So let's add them all up and see what we get. So negative 654 plus 579, I get a negative 75 joules. That will be the net heat flowing out. And negative 187 plus 112, I get negative 75 joules. That is the work done by the system to the environment. And then negative 467 minus 112 plus 579, 0, bingo. You better see 0 for total internal energy because you have a complete cycle. So the sum of all U's must be 0. So this proves that these two match, which is correct, and this must be 0, which is correct. Okay, so the net flow of work is negative 75, which means that the system is actually receiving work, or the environment is doing work to the system. And sum of Q, that means heat is now flowing out of the system rather than added to the system. Okay, so that's how this one works. So question number 51. A flexible balloon contains 0.350 moles of hydrogen sulfide gas. So we therefore need to look up the hydrogen sulfide gas. Some constants, hydrogen sulfide, CV is 25.95, Cp is 34.60, gamma is 1.33, just in case we need these. So that's from table. Okay, and then initially the hydrogen sulfide gas has a volume of, so V1, now 7 times 10 to the negative 3 centimeter cube. Now we don't like to work with centimeter cube, so you change that by writing times 10 to the, or 10 to the, oh sorry, this is 7 times 10 to the third cube, centimeter cube. And then you change centimeter cube to meter cube by multiplying by 10 to the negative 2 cube. Okay? That's because each centimeter is a 10 to the negative 2. But since it's cubed, so you cube it all. Which is same as saying 7 times 10 to the 3, and then just multiply any centimeter cube by 10 to the negative 6 to turn into a meter cube. So this question is the same as 7 times 10 to the negative 3 cubic meters now. Okay, 10 to the 3 times 10 to the negative 6 is 10 to the negative 3. Okay, so that's the volume given. And at the pressure of, at the temperature of 27 Celsius, which is 27 plus 273, 300 Kelvin, the HS first expands isobarically until the volume doubles. So V2 is double, that means 14 times 10 to the negative 3 cubic meter now. So it expands isobarically until it doubles. So if I were to draw some isothermals, so here is, but then since it expands, so I'm going to take this one as my V1, and this one's my V2. It looks like it's doubled. So it's going from here isobarically, goes to here, so from A to B. So this is the process from A to B. The pressure is, oh, we're not given the pressure, so we have to figure out what that pressure is. But the temperature at the beginning is, this is 300 K, so this is 300 K, and it's moved over to B. And then, isobarically to double the volume, and then it expands adiabatically until the temperature returns to initial temperature. Well, initial temperature simply means it goes back to 300 K. So from here to here, let's say here is my C, so it goes down towards C. So it's going down from B to C, has some volume 3, final volume. Okay, so part A, draw the diagram, which I just did. And B, what is the total heat supplied to the gas in the process? So Q, well actually you have to separate into two steps, okay? One is Q from A to B, and then Q from B to C. You have to add them all up to get the answer. From A to B, it's isobaric, so you should recall isobaric, you just need to know the temperature difference. But so in order to figure out the temperature, you need to know what temperature it will become. But we can figure out what this pressure is. Let's call it P1, which is P1 equals NR T1 over V1. We know the moles, we know the R is 8.3, T1 is 300, V1 is this number. So 7 times 10 to the negative 3 cubic meter, N is 0.35, R is 8.31, and T1 is 300. So we should be able to figure out what P1 is. So 0.35 times 8.31 times 300 divided by 7e to the negative 3. I get a pressure of 1.247 times 10 to the 5th Pascal. So that's the pressure. Okay. Now we can therefore figure out what's the new temperature here. The new temperature, which is T2, okay, call this one T2, which is going to be PV2 over NR. P is actually P1, the same P. So this is 147 times 10 to the 5th times V2, which is doubling this number, which is 14 times 10 to the negative 3, divided by N, 0.30, R, 8.31. So I get times 14 e to the negative 3 divided by 0.35 divided by 8.31. So I get exactly 600 Kelvin. So T2 is really 600 Kelvin. Now that I know T2, I can say, therefore, this number is 0.350 times CV, which is 25.95, times the change in temperature, which is 600 minus 300, which is another 300. So the heat there is 300 times 25.95 times 0.35. So I get the heat here. Well, let me just write it down here. So QAB is 2725 a joule. And the work, okay, so that's that. Sorry, this is internal energy. I need to add, okay, this is just internal energy. I need to add the P delta V, and P is this number, okay? So 1.247 times 10 to the 5th times the change in volume. My change in volume is just double minus itself, so it's just 7 times 10 to the negative 3 again. So this is the work done. And that will be 1.247 to the 5th times 7 to the negative 3. So I get 873 joule. So therefore, heat, QAB, is 2725 joule plus the work. So I get a total heat of 3598 joule. So 3598 joules is the heat from A to B. Now from B to C is adiabatic, which is 0. There is no heat added. So total heat, Q from A to C then is just 3598 joules, or 3600 joules. So that is part A, what is the total heat supplied. Part C, what is the change in internal energy of the whole thing. The internal energy in this first case is, well, internal energy only depends on the initial and final temperature. Since initial temperature and final temperature are the same, they're both 300 K, even though it has went through. But since we're only looking at the final temperature and the initial temperature, and they happen to be the same, so it will be 0, because that's basically NCV delta T. There's no change, so the internal change in internal energy should be 0. And part C, what is the total change in, oh sorry, that's part C. And part D is what is the total work. Total work, well, that means W. The first part we know is the area here, which is, we figured out right here, 873. Plus the work here. Now that's adiabatic, and the work done is NCV delta T, and that is the work done. Okay, in this case, N is 0.35, CV is 25.95, delta T, which is from 600 down to 300, so that's a change of 300. So we add all these up, 0.35 times 20.95 times 300, and then plus 873. Oh, wait, just a sec. 873 plus 0.35 times 25.95 times 300. I get a total of 3600 joule. So total work done is 3600 joules, and so that's total work done is 3600 joules. What is the final volume? What's the V3? Well, V3, we know the temperature, because we know that T1 V1 to the gamma minus 1 equals to T2 V2 to the gamma minus 1 for an adiabatic process. So assuming T1 is back in here, which is 600, V1 is really the 14. Okay, that's the V2 really. That's 14 times 10 to the negative 3 to the power of gamma minus 1 equals to T2, which we know is 300, times V2, which we don't know, to the gamma minus 1. So divide this one by 300, and then divide this one, over 14 times 10 to the negative 3, all to the power of gamma minus 1. So this is really 2. So this is 2. So you can now write 2 to the power of 1 over gamma minus 1 should be V2 over 14 times 10 to the negative 3. And 2 raised to the power of 1 divided by gamma is 1.33, minus 1 is 0.33. So the left hand side is 8.17. So V2 then is 8.17 times 14 to the power of negative 3. So I get 0.114 cubic meter. So the answer is 0.114 cubic meters, 3600 joules, and 3600 joules, correct. So that's correct for the total heat added and total work done is 3600, and the final volume is correct.